Good. All right. Gonna go ahead and start. Um, some background on me. Uh, my name is Ryan. I've been a system admin or cybersecurity expert for about 25 years. I started around 1994 messing with computers. I am 44 years old, so uh, you know that wasn't that long ago in my lifespan. I pretty much have looked like a nerd my entire life. So like I always joke that when I was born, the doctor like handed my mom me and was like, "Here's your little computer programmer," right? Glasses, basically born with a beard. It all worked out. Um, so in that history, I've worked for AT&T Lucent Bell Labs. I've worked for IBM. I've done some startup work. I've worked at a bank. I now work at a pharmaceutical software company that's based in California, which is probably the coolest of the jobs. Actually, I will say the startup I worked for in Columbus in the early 2000s called Starback was pretty cool. Uh, it was right before the bubble burst, so they were all like, "Yay, let's party!" Um, and then, of course, there was no money left. Originally, I'm from Boston, so yeah, that's about it. I generally don't use my real name for anything. So if you happen to know my real name, it's not a big secret, but for the most part, everybody just calls me Ryan Vile because, privacy mostly. No one needs to know my real name. So, anyways, boom, that's me. 25 years experience as either a system administrator or a cybersecurity expert. That CISSP is Certified Information System Security Professional. It's a very pain in your butt test that you have to take to prove that you're good at cybersecurity. It's about a 6-hour test. People take a whole year to sort of study for it. I studied and got that little title next to my name. Anyways, why Linux? By the way, just so you guys know, feel free to throw all the questions into the chat. I will answer them as I go. So why Linux? So 25 years in, I'll tell you there's always been a problem, which is people go to college, they learn programming, or they learn whatever they were there for, computer science, engineering, and then they go out in the real world and they're like, okay, my program doesn't work, and it's like, okay, well, let's go like debug it. And they're like, I don't know how to use Linux or Unix or any of it, right? And you're like, you didn't learn it in college? And they're like, no. And you're like, and you never thought you'd need it? And they're like, no. And you're like, crap. So 77% of all servers on the internet run Linux. So if you're going to write a application that's on the internet, it's probably going to run on Linux. And of course, 99% of mobile phones run either Android or iOS. Android is based on Linux. iOS is based on macOS, which is based on BSD, which is Unix, which is very similar to Linux. Okay. The good thing about Linux gives you unlimited transparency into what the computer is doing. So, if you go back to the 2000s and such, or the late 90s, or the 2010s, operating system providers have always been mostly keeping as much under the covers as possible, right? When you drag a file, you really don't see what's happening under the covers. Linux, you could definitely use it that way. You could use it like you would a normal desktop computer. and just avoid everything. Or if you want to copy files into certain places, you can go as low level as you want. You can use the CP command. You can literally use the DD command, the disk. I always call it the disk driver command. I don't know what it's called, to actually grab the sectors of the disk and put them over there, right? You can do all sorts of stuff in Linux that Microsoft really never planned to sort of show that to the end user. Another reason why you should learn Linux is now at this point, every job category in IT pretty much is now using Linux. If you're a programmer, as I said, like eventually someone's going to ask you to understand Linux. If you're a database administrator, you have to understand Linux or Unix. Interestingly enough, sort of in the past, there was only two people who really knew Unix. It was the database people and the Unix people. And the database people basically had to understand it because the only computers that were powerful enough to run some of these large databases were Unix. So all of the the good database administrators all understood Linux or some sort of Unix, because that's just what their database software ran on. Cybersecurity people now definitely have to understand Linux. It used to be that there was a lot more Windows on the desktop. Now the desktop computer is sort of going away. It's now a lot more laptops, a lot more MacBooks, a lot more thin clients that like you just like remote desktop into that run Linux. You got Chromebooks, all this stuff. And of course, your operations team also generally have to know Linux, because whereas if you go back 20 years ago, you had a lot of Windows. Now the operations people have to understand Linux instead of Windows. One important thing that I sort of glossed over, understanding Unix or Linux, they're sort of, I'm going to use them interchangeably. There's a difference. It's not important right now. Okay. So understanding Linux or Unix fundamentals is the same as understanding computer fundamentals. And so a lot of what I'm going to be explaining isn't necessarily going to be just Linux. It's going to be, how does computers work, right? Because most of the time, Linux or Unix derivative, some sort of operating system got things right, and then Microsoft or Apple sort of saw, oh, this is how other people are doing this. We should do this, right? Like, oh, we should pageify our memory. Oh, virtual memory. Oh, virtual drivers. All this stuff. It all came to Unix first before it got into the Microsoft space. And then, as I said, colleges do a crap job of teaching Linux. Boom. Going to go into some history. Again, feel free to interrupt in the chat. All right. So way back in the days, 1960s, before I was alive, right, large companies were buying computers to do their own accounting during the day, and then they were like, well, what are we going to do with this at night? And then, of course, there's people out there somewhere who are like, oh, we need this computer at night, but we don't need it during the day. And then, there's people, physics students who are like, we really don't care. We just need someone to do our math. And that's all computers are. They do our math for us, right? So starting in the 1960s to today, computer time sharing is big business, right? How do I find somebody to give me money for my computer when it's not doing anything? And you look at the 1960s and you're like, well, that made sense. And now you look at today with cloud computing, it's the exact same thing, except for instead of all of us sort of like going between each other, we're now just all going to Google or Amazon, and they're doing the time sharing, right? So during that time, 1960s, Bell Labs, GE, and MIT, they create Multics. Basically, Multics was supposed to be the industry leading of what is now cloud computing, but at that time is time sharing, right? And so all these smart people got together and they wrote Multics, and it was supposed to be the future, but unfortunately, uh, Multics just did too much. And what happened is Multics was very slow because everybody who had like something to say about how what the operating system should do and what features it should have got their word in, and it was bloated, and at that time Multics could not run fast enough, so they scrapped it. Ken Thompson basically goes back. He had what a lot of people don't realize, I think it was Ken Thompson, he had written a little game that ran on Multics. And then when they scrapped Multics, he was sort of like, but my game, right? So he goes in, he grabs like an old unused PDP computer, which at the time, not, I mean, it was decent, but it wasn't the best, right? And he writes Unix. Uh, Instead of Multics, it's Unix instead of multi-uni, right? And basically, he scrapped all the stuff, the bloated stuff, and created like a smaller operating system. And then Dennis Ritchie, also Bell Labs, who had created a programming language called C in 1973, he takes Ken Thompson's operating system and rewrites the whole thing in C. Uh, it was written in assembler, and that creates what is Unix, the 5th edition, or System 5. Right? Sorry about the history. We'll get through it quick. Okay. So now the source code's in C, and C is a language that people can easily read. And so Ken Thompson, I'm pretty sure it was Ken Thompson, happened to be out in Berkeley. And magically, who would have thought, another version of Unix comes out of Berkeley? So then all of a sudden you have the AT&T Bell Labs with System 5, and you have BSD coming out of Berkeley. So basically at that point, because the source code was mostly available, all these computer hardware platform makers like Sun Microsystems, Santa Cruz, Hewlett Packard, IBM, all these companies that basically sold large compute environments that are $50,000-$100,000 per computer. All of them grabbed that source code and modified it so that it would run on their platform, because at that time proprietary computing was a thing. There was no like, oh, I just buy this card and put it into my computer. All the computers were very different in that sort of big iron section. Anyways, we're finally caught up here. 1991, Linus Torvalds, just some like schmuck little student who basically is an undergrad. He's like, man, I want to write an operating system. So he goes and he takes the best parts of BSD and the best parts of System 5, and he creates Linux. And then he's like, well, cool, I did it. And he just says, you know what, guys? Have it. Here, right? I wrote this myself. I took all the stuff that I thought worked best in these other parts, and it's free. Okay? That changes everything, because there's one thing that hobby people love, it's free. And there's one thing that corporations love, it's free, right? So Linux all of a sudden is almost birthed out of the fact that it's free. So there's a few companies out there like Red Hat, Slackware, Debian. They basically take Linus's work, repackage it, and sell, and basically tell people like, yes, you can buy Linux from us, but you're not actually buying Linux. What you're buying is us supporting you, right? So if it doesn't work, you can call us. That's pretty handy, because just about every computer at some point stops working, right? And then, of course, we go forward a bazillion years, and mobile devices are the thing. Linux becomes the most used operating system in the world. Again, it's free. Linus Torvalds or Linus Torvalds, depending on how you want to pronounce it, it's free, right? Anyone can make a product out of it, and so that's what Google and a lot of these companies did is they went and they grabbed Linux, they modified it for themselves, and they made phones out of it. They made fire sticks out of it. Your thermostat, like just about anything now, it's all running Linux because not to say that Linus Torvalds didn't do a good job, but it's free, right? The one gotcha is if you are modifying it, your code modifications have to be available to other people. So if you decide to go change how the networking stack works, you have to make those changes available. So Linux now, as I said, 77% of the internet runs on Linux. So Ken Thompson and Dennis Ritchie, the creators of Unix, which would later become the parent to Linux, they look exactly how you think some like nerds in the 70s would look. And it's actually, so since my background, I worked with AT&T and Bell and Lucent. Uh, the interesting thing that you find when you go to those places is that a lot of these people who maybe worked at, like, we'll say AT&T or Western Electric or something like that, they worked on like the assembly line and they took a class on computers, and then they became like computer operators, and then like 5 years later they were system administrators. And you talk to them and you're like, yeah, what, you get their life story, and they're like, yeah, I worked at a steel mill, and then I worked on an assembly line, and then I took this class, right? So it all works out, right? Obviously, things have gotten a lot more complex, but all right. So when writing this operating system, there was some things that had to come in, sort of come to fruition. First of all, for time sharing computers, multi-user was very important. At that time, right, if two people were using the same computer, they were just stomping all over each other, right? I go to write to the disk as the same time as you go to write to the disk, and the spindle just, dies, right? I will say, so my first job in IT was I was a junior system administrator at AT&T, right? Slash Bell slash Lucent. And my job was they had computers that they had contractual obligations to keep running for 30 years, right? So imagine some guy wrote a contract or bought a piece of software in 1975, and here I am in 1998 trying to keep this 25-year-old computer still running. Right? So a lot of this stuff that I talk about, people think like, oh, it wasn't like that. No, it totally was like that. You totally had those giant disk drives. You totally had the big old tape reels. You totally had the old digital machines where to bootstrap it, you had to put the dip switches in the right way so it would know the first address to go to boot itself, right? Okay, so secure multi-user. Users can't stomp on each other, right? Second feature that was important for Linux was multi-process. And it's sort of the same thing, right? Like two users run two processes, they should not stomp on each other, but also one user should be able to run two processes, and it should not be able to stomp on each other. I should be able to edit a file and then in another terminal be able to do something totally different, right? That was something that was not common at that time. There was another operating system called VAX VMS, which was probably as close as you got, right? Remotely accessible, a big thing, right? If you're sharing compute time. You don't want the person to have to show up at your doorstep. So the modems and remote TTYs, right? So even back then, they would just run like giant long cables to go from data center A to data center B, and literally the only thing on that wire was almost like a teletype, and it had to be lightweight because they saw with Multics that if you tried to do too much, it failed miserably. Vax VMS, I would say, also sort of had that problem where it tried to do too much, and so it was just too stupidly expensive, right? All right, so those were the things that they wanted with Linux, right? So I'm going to talk about the internals of computers a little bit, and hopefully I don't lose anybody. And again, questions in the chat if you want, but feel free to not if you don't want. Okay, so in a long time ago, right? Even with the TRS-80s, they had an operating system, I think it was called OS8, right? If you wrote a bad program, your computer would basically just halt, right? If you tried to like write to the disk badly, the computer, you would just mess up the computer, right? Somebody had this great idea. Hey, why don't we put some sort of proxy in between the computer hardware and the user? And that's what we call an operating system, right? It is, instead of being like, oh, go peek and poke into this memory over there, you just tell the operating system, hey, I need some memory. And the operating system says, sure, here, right? Or you need to do some quick arithmetic. You tell the operating system, hey, go add these numbers together. And the operating system does it. It makes it so that you can't, it's much harder to mess things up for the entire computer. And also, it makes things easier as far as now I don't have to know about advanced memory structures to write a program. So, operating systems change everything. Unix specifically, because it was so, and Linux was so small and easy to see everything that it changes everything. People all of a sudden are like, oh, I can write an application in C, boo, 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 done, right? So, yeah, the application of the users talk to the kernel, and the kernel talks to the hardware resources, the CPU, the memory, the I/O, whether it be disk or network. And that keeps application, like for instance, if two people want to use the CPU at the same time, rather than them clogging things up, what happens is the kernel says, no, it's your turn. Okay, now it's your turn. Okay, now it's your turn. And then if you add another user, all of a sudden the kernel's like, okay, now we're doing this in threes. Now we're doing this in fours. Oh, this program is done. I can have that memory back. That is what the operating system is doing. It is just trying to manage A, what the users want, and B, the hardware of the computer. Boom. So we're going to start talking about processes. So anything that runs on Unix or Linux, it's called a process. If you kick off a program, it's a process. Every process has a user that is the owner, and only that user can interact with that process. So if Ryan kicks off, like let's say I'm reading my mail, so I type in mail, only I can interact with that. If John goes, writes a program and says like, oh, I want to see what's in the memory for that mail program, the kernel is going to stop them. It's going to say, hey, that process is owned by Ryan. That memory is owned by Ryan. Again, like operating system doing me a solid, right? There is one user on Linux called root, and they can interact with anything. They can do anything. So if you are writing Super secure sort of applications, you have to keep in mind that there's this root user that can break any permission you think actually exists, and then you have to do some stuff like encryption or something that root can't get past, right? Memory for a process is split between user space and kernel space. The user space is the stuff that your program is directly using. The kernel space is the memory that the process is using through the kernel to get to the hardware, right? So, like, for instance, if I'm like, oh, I need this file, the user space will be that file, but the kernel space will be like, where was that file located on the disk? What is the driver? That sort of stuff. Not super important to know, but it does sort of make things interesting. Okay, and the command ps is used to list processes. So I do have. Let me bring this up. I do have a Unix box that I keep. So PS, right? And it says bash and PS. Those are the two processes that I'm running right now, right? If I do ps-eaf, which gives me a view of everything, you see there's a lot more stuff, right? We have root, who's the super user, run a lot of stuff. I got Apache running some stuff. I have that KQ user, which I use for some bots. Cronny, so all sorts of stuff, all sorts of different users are running things on this machine. But if I simply do just a PS, I only see the stuff that I'm doing. And you actually can get a lot of information out of PS if you really want to. Like, for instance, when did this start? What is the process ID, which gives you some information about the order of operations of things started, how much CPU time it's used. So, like, if I like right here, like this bot really uses up a lot of CPU time. I'm not sure what it's doing, and I don't really care. But that might be something that was interesting to you, right? So PS is used to view processes. Boom. All right. So we've talked about processes. We're going to talk about the CPU a little bit. So if we go back, hold on, let me take a sip real quick. Okay. So I was talking earlier about how, let me go backwards one. If two users want to use the CPU at the same exact time, and let's say there's only one CPU, the operating system has to divvy that up. And that's where we start talking about scheduling. So there has been many attempts at a fair scheduling system. Generally, engineers, we use elevators and staircases as sort of our real world metaphors, because you know how, like, you're going up a staircase and there's somebody in the way, and you're like, well, crap. I mean, please. And elevators are sort of the same thing. Like, it blows my mind how complex elevator scheduling has to be, because you think about, okay, I'm on the top floor, I hit the button, but all the people under me, if they hit the button, they might just get picked up every time before it ever gets to me, right? And that's something that used to happen with time sharing, and now they've sort of realized, oh, we need to figure out a way to do this, right? And that's why elevators way back in the day had an elevator guy, because that guy would just know. He was smart to be like, you know what? I have not been at the top floor in a long time, but I know somebody hit that button, right? But now a computer can do that. Okay, but you can't just say, like, okay, next person up, because it could be inefficient. But you also can't just say, okay, which one is the most efficient, because that leaves off the people that are sitting at the top and the bottom, right? If I'm at the 5th floor, the most efficient way for me to travel is between the 2 floors below and the 2 floors high. So you have to come up with this scheduler, right? So a process inside of a process, there's what's called a lightweight process. So a process can have 2 threads at once. Those are called lightweight processes. Some people call them threads. They're basically the same thing. So when it starts up, it's assigned a CPU. And then as more processes start up, the CPU starts getting divided. The problem there is once the CPU starts getting divided, so how a computer works, right? You have, your CPU and you have your 16 gig of memory, right? But on your CPU itself, it has a tiny bit of memory. And really, that 16 gigs of memory you have out there, that's all that's happening with that. That's almost like a cache, right? Where it's going to grab some stuff off that. It's going to put it on your CPU. It's going to do that math. And then when it needs to cycle to a different process, what happens is it has to go grab more stuff off that RAM, put it onto the CPU and do more math, right? That's all CPUs do is math. A lot of people think like it's really complex. Now it's just math, right? And you don't even have to know the math because the computer does it for you. That's the best part, right? So anyways, it gets very inefficient if, like, for instance, if there's 2 processes running and one of them is pretty close to finishing, but you keep on taking its context off of the CPU and putting it into, and then grabbing, the other process, putting that on the CPU, right? And so there's a lot of push and pull with the scheduler. So, for instance, a lot of times what'll happen is, like, let's say your CPU is like, oh, well, or your process is like, oh, I need to get this file off of the disk. The CPU is very smart. It's like, dude, that's going to take freaking forever. You know what? You chill out over there. You just chill out, dude, while I get this. But you guys over here, right? You guys who've been chomping at the bit to do some math, come here. I'll do your math while I'm waiting for that disk, right? But then if my process really uses a lot of disk, it's always getting put on the back burner, and it's sort of pissed because it's not getting as many cycles. It's like, oh, hey, I'm here. Oh, yeah, I do need disk. Wait, no. Oh, man, I'm off the CPU, right? So the scheduler also takes care of being like, you know what? I'm always sending you off and waiting. Like, let me give you a little love right here. But there's also different use cases for different schedulers based on how you use your computer. A server, right? You definitely want it sort of being a little more fair, but a computer that you're sitting down and using the user interface, right? You want it to give the window that you're in more CPU than the window that you're not using, right? So which is totally different than the use case on like a server, and totally, your phone, which also, by the way, has a scheduler, probably the completely fair scheduler because it probably runs Linux. It probably has a little modification that says like, oh yeah, when the application is up, give that guy more time on the CPU, and if it needs to go talk to the cloud, throw it off in the back burner and give some CPU to one of my other programs. So that, and I realize this is like a Linux course, right? But it's important to understand that like all computers do this, whether they run Linux, whether they run Microsoft or VMS. This was the right thing. And when they figured out like, oh, this is how we need to do CPU cycling, everyone else started doing it, right? And there's just little modifications based on your uses, right? So understanding how the scheduler works, actually gives you a good understanding of why your stupid freaking phone, one application is just sitting there in the void. It probably wanted to talk to the cloud or something, and your phone operating system was like, well, I'm not going to give you any CPU cycles for a little while, right? So, all right. So next, we're going to talk about virtual memory. So generally, when people talk about memory on a computer, they almost always mean RAM. They don't mean the storage, as in the hard disk. They mean the RAM. But the funny thing is, if you really, really sit down and think about it, the memory, the CPU cache, right, is on the CPU. It is the fastest, right? And then the RAM is pretty fast. And then there's a disk, which is really slow. So if you're using more memory than you have, and your operating system's like, hold on, I need to take some of this and put this on the disk, and then so I can run this other stuff. Everything got real slow. And this was the thing that happened in the past a lot. I think now that the cost of memory has sort of dipped so much, uh, it's not the same. But you never wanted swapping in the past. Interestingly enough, now disk speed is way faster, but so is CPU speed, and so is RAM. You're seeing a lot more layers where it's like, okay, you have the CPU level 1, you have the CPU level 2, then you have the RAM, and then you might have like some solid state disk that acts as a swap, and then you might have some magnetic disk that acts as like your big disk, and all of that together like works in this weird system where the things that are used the most are supposed to, float to the top, and the stuff that you never use is supposed to end up on the slowest disk. That is the way it's supposed to work, right? But so if we go back to this chart right here, we have memory, right? Um, Again, way back in the days, if you wanted to access the memory, you were doing what, peeks and pokes. You were basically being like, throw this into this part of the memory, throw this into this part of the memory, throw this into this part of the memory. Oh, okay, give it back. Okay, put this. I added this in this, and this equals this. Put this in there, right? Really, that it was a you you couldn't really find programmers enough smart programmers to really make that a feasible model. Everybody knowing exactly what memory addresses go to what thing and the hardware. So they created what's called virtual memory. So at that point, the programs have absolutely no idea what's going on. The programs are just like, I need some memory, and the kernel is just like, here's some memory. Now, that memory could be on RAM, it could be on a swap disk, it could be on the moon. The application, it has no idea. I mean, you'll know because your application is like sluggish as heck, and you're like, oh, why is this thing on swap, right? So it made it so that programmers could very easily write an application because it's like, oh, I'm going to need this file in memory, and the operating system takes care of it rather than me writing a disk driver to go get the file off of the floppy, right? There's three kinds of memory. There's resident memory, which is the memory that's being used at that very moment, right? If I look at my phone, it says 8:36 and the date and some other things, 8:37. That must all be in resident memory because I'm looking at it pretty much right now. Virtual memory is the total amount of memory that's been allocated for the process, whether it's used or not. So, for instance, if my application every 10 minutes, or we'll say every minute, needs to go connect up to the New York Stock Exchange and pull down a gig of stock info, the resident memory most of the time is going to be small, but then uh, once a minute, all of a sudden the memory peaks, right? And so what the operating system does is say like, okay, this person is using a gig of memory every minute. So let's just keep them with a gig, but the amount that they're using right now is a very small amount. But we know for a fact that they're going to be using a gig. So if anyone else tries to get a gig themselves, let's just avoid them running into each other. You know, uh, we now know, okay, this person's using a gig, this person's using a gig. I only have one gig, therefore I'm doing swap over here. That's very bad. There's one other kind called shared memory. So the best example I always give of this is, let's say you read a file and it's 1 gig, right? So you read in this 1 gig file. Your program is called program.sh, and it reads in 1 gig file. And then me over here, my name's Joe. I'm a totally different person, but I happen to be writing an application that also reads that exact same file, right? So you have Ryan, who's reading a 1 gig file, and Joe, who's reading the exact same 1 gig file. Now, you go back in the old days, it's rough because you got 2 applications, each with 1 gig of memory. But virtual memory and shared memory sort of fix that, where it's like, okay, rather than 2 gigs, we just create a shared memory segment, and anytime somebody changes that file, we just change that memory, and anytime one of those guys reads that file, it's going from that shared memory. Now, this is assuming that they both have access to that file. Remember, one of the things that we talked about is secure multi-user. So there are permissions to files, and in this use case, in this example, both people need to have access to that file, which we'll talk about that in a bit. Just so you know, if you're programming in Java, Java, it's generally its own beast. It will basically go to the kernel and say, like, hey, these guys told me I need 32 gigs of memory, so give me my 32 gigs of memory. Shut up, right? I don't want you to do any of this other stuff, operating system. My name is Java. I'm going to do my own thing. Which is interesting because it's almost like virtual memory inside of virtual memory. Java being the most ubiquitous programming languages at this point, a lot of people are just used to letting Java do its own thing. It does a lot of the same stuff that virtual memory does, but it just does it inside of itself, right? It's almost like a virtual machine inside of a virtual machine. All right. So inside Java, by the way, it does this thing called garbage collection, and we're going to talk about what's called the Slab Allocator, which is very similar to the Java garbage collection, right? All right. So prior to somebody in Sun Microsystems inventing the Slab Allocator, freed memory is freed up as it became available, right? I am process number 1. I used 1 gig of memory. Oh, I am done, right? And immediately the operating system would be like, cool, and clear out all that memory. Well, if you're doing a lot of programs that use a lot of memory and then go away, what they found out was, man, we spent a lot of time just like freeing up memory, right? So the slab allocator basically, first, one of the big things it did is it broke memory into pages, right? So instead of me being like, I need 15 bytes of memory, the operating system would just be like, you need 15 bytes. I don't care. You get 1K. You get 1,000. You need 20 bytes. I don't care. You get 1,000, right? None of this willy-nilly, like, oh, whatever. You need this much. No, whatever. You're getting this much. You're getting a page so that I can very easily sort of manage who's doing what. I know you have 1,000. I know you have 1,000, and 1,000 is really easy to add. 1,000, 2,000, 3,000, compared to 15, 23, 17. And so they made these pages of memory. And there's different page sizes based on how much memory the application thinks it's going to need. So if the application is like, I'm going to need 500 megs, the page size there might be 200 meg or something. So you end up with 600. You end up with 3 pages of 200 megs each. That would be a giant page, but probably they do that these days now that memory is so cheap. Okay, and so basically what happens is rather than things sort of being like, hey, I'm done, and the operating system clearing out that memory, the slab allocator just on a schedule just goes through and says like, is anybody using this? No, okay, it's cool. Anyone using this? Yeah, okay, we have to keep it. Anyone using this? Nope, let's get rid of it, right? And it also tracks which objects stay in the CPU cache and attempts to not overwrite that area. So we were talking before about how like in the scheduler, right? Every time there's what's called a context switch, the computer will take some of the memory off and pull in some new stuff, right? It with a very good memory management and multiple CPU cores and CPU caches like modern computers do, a lot of times the slab allocator will be like, you know what? Let's put this person over here because it will keep the CPU, the memory on that CPU, fresh instead of having to swap it into memory, swap it into RAM, and then swap it back. Right? Slab allocator, man. It was great. It was a great invention. Yeah, love it. All right. So now we're going to talk about the file system. So everything in Unix is a file, even devices. So I'm going to give sort of an example. I'll do this over here, right? So this is my little box sitting in the wild there. There's a box called, or there's a directory or a folder if you're a Windows person. I don't care what you call it. Some people like to call them labels. I don't even think that's right, but people do it these days. People are weird. But anyways, so there's a bunch of devices in here, right? But they look like files. Like if I was going to echo Ryan rules dev, it's gonna come back and say it's probably gonna say permission denied. Yeah, but oh, how about this sudo? All right. Oh, it still did it. Oh, I know why. Doesn't matter. We're not going to get into the engineering. But you basically, instead of having to write device drivers for your program, you literally just open up a file in your program and say, hey, I need to write to the console. And so I open up dev console. Oh, I need to make a beep. Well, I open up dev beep. I don't think dev beep exists anymore, but it used to. In this case, so yeah, you want to make a sound, write to dev sound. Want to write to the network? Dev. Let's take a look here. Config. Let's see. So I have a single network interface. Oh, where is it? Find dot. You guys might be making me a liar. Oh, yeah, it's not there. Weird. Okay. Anyways, normally you would, if you want to write to the network, you would write to like the F0 device driver or file. If you want to look at the process table, you could just do this, right? If I want to look, right, but let's say I wanted a little more details. Everything is a file, right? So if I need to look at how much memory is permission denied, sudo cat mem. Man, I did not prep myself well. Hold on. Cat mem. Input output error. Yeah. Trying to find a good example here. Slab info. Yeah. Okay. Yeah. So this would be all these slabs that are in memory, since I just talked about the slab allocator, right? Uptime, sudo cat uptime. How long's the server been up? Oh my gosh, what does that even mean? I know what that means. You don't need it's dumb. Okay, anyways, every file has an owner and a group, and a directory is just a table that contains a list of file names and the inode. And the inode just contains the permissions of the file as well as the disk location. So if I look at a specific file, right? In this case, I was looking at list.txt, right? I know it's 194 bytes, which is 8 blocks, which is very similar to pages. Uh, IO block size of 4096. Again, very similar to page size. It tells me what device it is, tells me what inode it is, how many files are pointed to it, that it's owned by me, my user, my group, and then there's all these dates, right? Like last time these files were used. Obviously, I do not use this machine very often. If the last time I looked at list.txt was sometime around 2016, right? I would probably remove that file. But so it's important to understand that everything's a file, and every file has an owner, which is a user, and a group, and a permission for everybody. So let's talk about permissions. This is the part where people hate Unix, is the permissions, because Unix was written for engineers, and while once you understand it, it's not that hard. It's just not as easily digestible as right click and do a thing. So if we look at, so normally a permission, so let's take a look at a file here, right? There you go. There's that stat list.txt. Okay. So if we look over here, we have access 0664 right here. And we can also do just a ls-l list.txt. It does the same thing. This is a little bit easier to read. So I guess we'll look at this one, right? So it says read, write, read. And it's 3 sections. There's 3 categories: user, group, everyone. Read, write for user, read, write for group, and then read for everyone. 0664. So read plus write. Oh, wait, sorry. Read 4 plus write 6, right? If it was read and execute, 4 plus 1 would be 5. If it was just execute, it would be 1. In this case, we're at 664. So we have read plus write, 4 plus 2, which is 6. And then we have read plus write, 4 plus 2, 6. And then we have read, which is 4. 664. Now, the funny thing is, you could actually get along pretty well without ever knowing how that works, because let's say, so I just changed the permissions. I got rid of the ability for Ryan to read or write that file as a user. The funny thing is, I'm also in a group called Ryan that has access, but that's a whole nother complexity. So notice I didn't use any of those numbers, right? You could get along just fine without using those numbers, but at the end of the day, like let's say, at the end of the day, you end up just learning it as you go, and it's not as complex as you would think, right? You're just like, oh, because there's a few that you almost always use, right? So 755 list dot text, right? So it's read, write, execute, read, execute, read, execute. So the owner of this file, which is Ryan, can write the file. Anyone else can read or execute the file. Now, this is a text file, so obviously it will never be executed. It's not a program. So if I was going to be proper, I would probably do 4, right? So now, read, write, execute. I don't know why I kept execute on that one. I guess doesn't really matter. And then just read on these two. One interesting thing is directories. Like, right, so I have this directory that's read, write, executable by me, and then read and executable by everybody. With a directory, the execute bit, this little 1 or the X, it means someone can access it but not read it, right? So if I was like cat test directory file.txt, if I had just execute permission of test directory, I couldn't tell if file.txt existed, but if I knew file.txt existed, I could access it, assuming I had permissions to file.txt. So you can't read what's in the directory, but if there's a file in there that you have access to, it will let you get to that file if there's an execute bit. File permissions, always the most complicated part, and honestly, over the years, they become less and less important. Because most of the time, people are now building servers for like one use and one user, right? It used to be you built a Unix server and there was like 17 applications and 3,000 users, and Joe is trying to do his math homework while John is like, trying to write a program. It doesn't work that way anymore. Like pretty much everyone just has their own little Unix now, so no one cares about permissions. But you still need to know them if something's broken. So the basic interface to Linux is called the shell. So if you've noticed, I've been typing into this. This is the shell. It looks a lot like a mainframe, right? Like except for it's not capital letters, but for the most part, yeah. And that is your interface to the operating system. So in Windows, of course, we have, the DOS prompt, right? In Linux, instead of the command prompt, you have the shell. Most Linux systems, it will be a bash shell. I know the MacBooks now use a ZSH shell. For the most part, until you're like programming in shell itself, you really don't need to know the difference, right? It always works. And the best thing about the shell is you can use the tab button to, let's see, to just do search and replaces, right? So in this case, my old band's website and then a backup, right? Yeah, so yeah, okay. Oh, backwards. Okay, so most shell commands have very short names. So again, if we go back to Multics and Unix, they needed to get rid of a lot of memory they were using. So the editor was called ed to copy a file. In command, it's copy, but in Unix, it's just CP. To rename a file instead of rename, it's just MV, right? Very, very short names. You can, one of the most powerful things is also you can pipe things. A lot of people don't know what the pipe character is. If you hold down Shift on your keyboard and backslash, so a backslash goes from the top left to the lower right, whereas a forward slash bottom left top right? The forward slash is in dates. Backslash is used in Windows a lot, like Microsoft operating systems. Anyways, but if you hold down Shift and hit your backspace, you get what looks like a straight line. And you can actually pipe one command into another. Rep Ryan. So in this case, if I just cat etc password, it gives me a bunch of stuff, right? But then I put a pipe character and I put grep Ryan at the end. It takes the output of cat etc password and pipes it into grep Ryan, and I get what is basically a search, right? This is gonna go okay. Yeah. Oh, and that's an example there. You can also redirect things. So again, like cat etc password Ryan.text. So in this case, instead of a pipe, I use an alligator. If I look at Ryan.text, it is the same exact thing that was output from cat etc password. I can keep going though, right? I could do grep Ryan. So in this case, I take cat etc password, I pipe it into grep Ryan, and then I redirect the output into Ryan.text. Sorry, all the beeping. It's Unix people just get used to it. And boom, right? It's the output of this, grep of this, and then output there. There's a lot of that. There's a lot, right? If for instance you're like, oh man, I need to know what day of the week it was, or day of the month, or something. I don't know. Apparently it's May. I don't know what capital M is. Oh, is that minute? Yeah, I bet it is. So you can do stuff like, okay, I need to know like cat etc password into Ryan dot we'll do this text. Now, oh, that didn't work the way I thought it would. But anyways, oh wait, no, it did work exactly how I thought it would, because it just changed the time, right? It's now 00 minutes rather than 59. If we did that same thing and we did a month, boom, there's Brian 05 text, right? So you can start like using those little features to sort of create a full featured like task very quickly, compared to like PowerShell and things like that. Shell script generally is a little more friendly for people because you get used to it pretty quick. All right, I have this slide, which is the worst. Okay, so Unix was invented before, and computers reliably had monitors, right? And a lot of people got used to the ed command. I couldn't even tell you how to use the ed command, but basically, imagine trying to edit a file where every time you looked at it, it would print it out of an actual printer. And so people got really good at using ed and making sure that they could basically edit things line by line. But what ends up happening, of course, is engineers are smart, and someone, learns like, oh, we could just hook a TV up to this thing, right? Like we could have a monitor, right? A monitor. So they needed another editor that was visual, and they very much appreciated ed, and so they created VI. And if you're a Columbus person, Columbus, Ohio, one of the authors of VI is Mary Ann Horton. She's now out in the Bay Area, as any engineer should be. And but she used to give talks way back in the days about VI. She also went to Berkeley, so and smart lady. But she actually helped write VI, and she lived in Columbus. And VI is probably the most useful yet hard to manage tool uh, in Linux. Let me see if I have a file that I can just do. Sorry, looking. Yeah, I don't have any like weird files. I can just add 52. All right. Well, we'll just create one real quick. Vi text. All right, done. Boom, I got a file. So with VI, like back in the days, they would move around with the HJ, JK, semicolon, J and K, and then L and semicolon. Wait, is it semicolon? I don't know. These days, I always just use the arrow keys, but they didn't have them back then. And so they created this editor that was super quick to do a lot of stuff, but it was super painful to do little things. Like if I just wanted to, go up 2 lines and write something, right? I have to like hit up arrow twice and then an I and then type my stuff and then hit escape. It's a real pain, but you can also do stuff like very quickly do search and replaces, things like that. So it's super powerful. You just can't type though. You have to go into insert mode. And many people just get stuck in VI because they don't know how to get out. That's another thing. You can't Control C out. This version on modern Linux is actually super helpful because it's like, hey, do this to get out of here, right? Type QA if you want out, and that's the same thing I wrote over here. If you need to get out, just colon Q exclamation, right? That's not easy, right? And so if you happen to be working on Linux and you're like, oh crap, I have to edit a file, dude, just there's another one called Nano, Nano, and it is more like user friendly. It just doesn't have all the power. When I started as a system administrator, I wasn't very good at VI. It's something you just had to use a lot. And so I would log into servers when people weren't noticing and like load up Nano, or actually at that time it was Pico, which was another editor that was very easy to use. And then occasionally people be like, how did Pico end up on this server? And be like, I don't know. You know, the old days. Anyways, the most important part about VI that I can tell you is it's hard. Don't if it's the boundary in between you using Linux, just don't. Right? Just don't. Anyways, that was my whole presentation. I do have some resources. Let me find. Yeah. Okay, I need to paste these into the chat real quick. Boop boop boo. Let's see. All right. So one of the easiest ways, it used to be like if you wanted to learn Linux, you would have to take a computer and load Linux on it. These days with virtualization, you could just go get VirtualBox from virtualbox.org, and then load any operating system that you want to play with, right? Just go search like Linux, right? And just find any of them will do, right? There's a million versions of Linux out there, all of them a little bit different. Just find the free one, right? Fedora is a good one. Ubuntu is a good one. People freaking love Ubuntu. People love Arch Linux. Like all these people. There's so many like different variations because engineers are picky. There's also you could actually on your Windows 10 machine, you can literally basically load a Ubuntu subsystem. So it's called WSL2 on Windows 10. I personally have never tried it, but I have coworkers that use it. I have a Mac at work, so I don't have to load Unix onto it because Macs are already based on Unix. You could also just go if you wanted to like play with Linux in the cloud. Amazon Web Services, Google, Microsoft Azure, they all want you to use them and they will definitely let you use them for free because they in the long run need people to understand their technology, right? It's much like when I was a kid, um, we would have to take shopping receipts and send them off to Apple, and then Apple would send your school a bunch of computers, and you were like, cool, free computers. But actually, like, Apple was basically trying to make sure that people grew up learning Apple computers. And once Microsoft got hip to that game, they changed their pricing pattern and were like, oh, yeah, it's free. Microsoft's free in schools, right? So everyone coming out of the education system, all of a sudden, they all knew Microsoft products, right? Uh, there probably is. Uh, I'm not sure. So the question is, isn't there a resource that enables you to quickly load and unload different distros? So different versions of Linux are called different distros. There probably is. I mean, generally you could just go download them from multiple and then run them inside VirtualBox and decide which one's the one you like. Uh, People can get very opinionated over which one is the best, and I'll tell you, none of them are the best except for like the one that you have to use at that time, right? Like, if I'm working in the Amazon cloud, I'm using Amazon's version of Linux, right? If I'm working in Alibaba cloud, magically, I'm using Alien Linux, right? Which is the uh, China's version of their cloud provider. And then all of a sudden, I'm in Azure and I'm using CentOS because Microsoft likes you to use CentOS, right? Um, they're all the same. Like it's like comparing a Ford to a Dodge to a Plymouth to a Honda. Like they all have um, their pluses and minuses, and if you ask certain people, they have very strong opinions. But if you're the mechanic or you're the driver or whatever is given to you is the one you got to use, right? Another really cool thing is the Raspberry Pi. So Raspberry Pi is a little $40 tiny little computer, and probably a little more expensive because of the chip shortage. But it's basically a little tiny computer, 45 bucks. No screen, no nothing, but you can just plug it in to your network or configure the Wi-Fi on it, and you magically have a tiny computer that you can program to do stuff. So, for instance, the if you go to a brewery, a lot of time they have these signs of all these beers that they have and all this information, and it magically gets kept up to date with their website and blah blah blah. It's just a stupid little Raspberry Pi with a little browser on it, and they plugged it into the back of their TV. uh, and that's all it does. Raspberry Pi is super handy. For instance, I've used it for putting um, music in bathrooms, right? I've used it for monitoring networks. I've used it for bridging networks. I've used it for all sorts of stuff, right? Right now, I have a couple of them. They just sit in some arcade cabinets, right? Yeah, you can actually build all sorts of stuff on Raspberry Pi. So the hardest part about learning any sort of skill is finding a project to do, right? It's one thing to say, oh, I need to learn Linux. You generally need to find a project. And if you want to like program something, like if you want to program a website, probably the cloud is the way to go. If you want to program something that's a little more, hands on, then probably a Raspberry Pi. If uh, maybe you're just like trying to do some phone development, then maybe local machine, VirtualBox, and then there's a lot of like phone emulators out there that you can just load on. So I think that's about it. I'm actually, unless someone tells me otherwise, I'm probably gonna move these to Thursdays. When I first invented Tuesdays, Tuesday was open, but Tuesday is no longer open for me. So, uh, besides that, if you need to get a hold of me, if you can find me on Facebook, but also ryanvile@gmail.com, that goes to me. And I think that's about it. So I appreciate everybody sticking around, talking in the chat. That sort of thing is appreciated. I've actually given a lot of presentations in my life, uh, probably over 200 or 300. So I'm sort of used to just talking to nobody. But it's nice to be able to look out of the corner of your eye and see like, oh no, people are talking about stuff. That's really cool. So I very much appreciate it. The next one will be I'm going to go over TCP/IP, which is what the internet runs on. It's going to give you a really good breakdown of sort of how things work on the internet, right? So we now hopefully you've got a pretty decent understanding of how computers work. And then the next step, of course, is what happens when you plug it into the internet, and that will go over TCP/IP. I'm gonna have to go through my slides, make sure get them up to date, but that will be in June, first Thursday in June probably, and then after that, I am probably gonna do the cloud. I'm probably gonna do AWS because AWS Amazon does give out a lot of credits and a lot of free tier type stuff. So it's a really good place to learn. I like Google as well, but like right now, Amazon sort of has the advantage as far as if you were going to work in the cloud. Amazon seems to be the biggest contender. So appreciate everybody, and I'm gonna go feed my cat and eat dinner. So thanks everybody. Have a good night.